Okay. What are the two criteria for an effective brace? What are the two things we have to have for a brace?
Resist twist and lateral movement.
That's right. We need to resist twist and we need to resist lateral movement. Two different criteria. Okay, so I've got a beam here that's loaded and I have that brace. Is that an effective brace? Let's say it's at the middle. Okay, is that going to be an effective brace? Why not? Does it resist twist? Does it even resist lateral movement? What wants to move laterally? Why? To compression. And we're bracing the bottom. Doesn't work. This is not an effective brace. How about this one? How come? Yeah. Okay. How about that one? Okay, so now I'm loading in the opposite direction. So now I have a brace at the bottom. And the answer was given was, as long as this is a shallow beam, we're good. That's right. As long as it's a shallow beam, it's good. He said, what? But you're bracing the bottom flange. Yeah, but it's the compression flange now, isn't it? Okay, so how about this? Is it going to be good or is it not? It's going to be good for shallow beams. How about deep beams? That's stiffener. Yes. Yes. Yes, it will. So when something's an effective brace, then you could actually assume that the L sub B was, that distance, right? If it's not an effective brace, you ignore the stiffener. Hopefully, if you're designing, you don't use things like that, not stiffeners, braces. You don't use braces like that. Right? You think about, you understand the system, and you go from there. Okay, so now how about if I do this? No. It's just actually going to rotate around the brace, isn't it? Okay, so how about this? That's a deep one. The brace at the top. Not good enough, is it? How do I brace this? I could add a stiffener. What else could I do? Could brace the bottom. Okay, so now you have a miniature homework. You have to go out and find two examples of bracing. And you have to take this picture of the same set of bracing from two different perspectives. That keeps you from going on the internet and downloading pictures. Okay? So you're going to find bracing. I don't really care if they're effective or they're not, okay? I mean, we're just trying to find a brace on a beam, okay? And I want you to take pictures of them, okay? And email them to me. Two different bracing systems, okay? From two different perspectives, okay? Does that make sense? And then write up whether you think it's an effective brace or not for that situation. You with me? Okay. It'll be due. Let's have it be due next Friday. Okay, so we're not going to quite leave the world of bracing yet. We kind of are and we're kind of not. Okay, so don't forget any of these things that we talked about. Don't forget. So now I'm going to say, what is C sub B? What is the C sub B factor? What's it all about? What's the C sub B factor? What is Toby Brown carrying? It's the guy out there in the hall. He's my neighbor. What's the C sub B factor? What's it for? Man. C/B factor. Okay. So first of all, you're right on the right path. It adjusts the moment capacity for what failure mode? Okay. Let's go backwards. What's the label on the y-axis? What's the label on the x-axis? LB. At least it is for rolled sections for this first snail chart. Remember, we have introduced 2 other snail charts, right? And remind me, and I'll show you that page in the book where those other gamma factors are. Okay. But this is the first snail chart, right? First snail chart of apocalypse, right? And in this zone, what was the failure mode? Plastic hinge. And in these 2 zones, what are the failure modes? Lateral torsional buckling. One's inelastic and one's elastic. Correct? Right. Now, what does the C/B factor help us with? Plastic hinges? Oh, you're killing my heart! What does the C/B factor help us with? Oh, I'm dying! Come on! Yeah. Cannot increase above FEMCP, can we? Ever. No, it doesn't help at all in this zone. C/B does nothing in this zone. Oh. How about this zone? Yes. How about in this zone? Yes. What is C/B about? What is it all for? Well, it's because when we derived lateral torsional buckling equations, when we derived those failure modes, we assumed what about the moment? It's constant. We assumed a constant moment. Do we always have constant moments? No. So the C/B factor, does it make our capacity go down or up? Always up. Always up. How high can it make it go? Can never, ever go higher than FEMCP. Ever. So, what the C/B factor does is it's this factor that takes into account that, in fact, we do have a non-linear moment diagram on our cross-section, along the length. Why that's important is that, man, I don't have those notes, but along our length, if we have a constant moment along our length, constant moment diagram, that doesn't happen ever, okay? But let's say, it does, it can happen. Say we have a constant moment along our length, okay? What that means is that the top flange constantly has the same stress, doesn't it? All along the length. Okay, if we have a case where we do not have a constant moment along the entire length, okay, then that means that, let's say we now have a beam, or maybe only the constant moment's high here, and it's not high here, or here. You with me? Then this section might want to buckle, but this section says, I don't think so. I don't want to buckle. So what does it do? It helps. It actually helps restrain this material in the center. It helps restrain this length that really wants to buckle. Because of that, it increases the capacity. And because of that, to traditionally do lateral torsional buckling in complicated problems exactly requires 5 pages of nasty differential equations. Not just differential equations, nasty differential equations. Okay? That you have to solve. Okay? I don't want to do that. Not just to solve one of these problems. So what they've done instead is they've introduced this concept called C sub B. And what the C sub B factor does is it increases the moment capacity, but it can never, ever, ever, ever increase it higher than phi m sub p. That is extremely important and something that you need to understand. You with me? Okay. Yes. Okay. Now, let's turn to this sheet about what is C sub B. So for all previously presented equations were derived for a beam under a constant moment. All those lateral torsional buckling equations were derived for a constant moment. If the moment diagram is not constant, which it rarely is, then one can increase the predicted moment capacity by the C sub B equation. However, one must be sure to not increase the moment capacity above phi m p. Why not? Because it's a plastic hinge formation. C sub B helps us with buckling. It's derived for buckling. It's all about buckling. If you get to the point where plastic hinge, you're increasing your capacity above phi m sub p, that is wrong. You can't do that. That is the cap. That is the ceiling. You will never be able to go above that. Okay? This is twice I've said it. Okay? Okay, and this shouldn't be the first time you've seen that. Okay? You should have seen that before. For all of you that had me, I know you've seen it before. Okay? Might not remember it, but you've seen it. Okay, now what we're going to introduce is we're going to introduce this really cool equation. It's pretty cool, at least, that takes this very complicated situation and boils it down and gets you an answer that's pretty close. Now, I'm not even going to pretend that these answers are dead on. They're not. They are not. So when I calculate a C sub B factor of 1.14, it doesn't mean that I would expect it to be the capacity to be exactly 14% above what the equation, normal equation, would tell us. We are simplifying so much here into one single equation that we would not expect. We'll always expect it to be conservative, but we do not expect it to be accurate. You with me on that? If you want accuracy, what do you got to do? 5 pages of differential equations. Maybe even some of these are like 8 pages of differential equations. Okay? Fun. No. So, but there was a time when I thought that was fun. Anyway, for the C sub B equation, what is it? What is it all about? Well, first of all, you always use, and we're going to actually introduce, this is a C sub B equation you should have seen before. Every one of you should have seen this before. Okay? And we're going to introduce this one, and then we're going to introduce 2 more special circumstances that are not typically taught. If you've seen them before, I'd be shocked. Okay? You should have, but they're just not in the manual. There's just not enough time. So you'll learn them in an advanced deal. C sub B. How does it work? First of all, you always use absolute values for all the m's. In these, not in every one. In these, every single C sub B is going to have its own set of rules. But in this set of C sub B calculations, you will be using absolute values. Okay, so here's the moment diagram. Okay, we're going to be picking off something called M sub A, M sub B, and M sub C. That's the moment at the quarter, the half, and the 3/4 point. Hey, this one's negative. What value do you use? Positive. right? Oh, I guess I'll just have to start singing again. Get you guys to pay attention. And this, what's this? M max. Doesn't matter if it's positive or if it's negative. You're always going to use a positive value for it. You with me? Okay. You plug into this equation. 12.5 times M max over 2.5 times M max plus 3 times MA, 4 times MB, plus 3 times MC, all times R sub M. Guess what? In undergraduate class, you got to assume that R sub M was 1 for a doubly symmetric shaped member. If you have a singly symmetric member, something that looks like this, singly symmetric, it's symmetric around that line, it's not symmetric around any other line, then this is added to it. 0.5 plus 2 IY sub C divided by IY. This is IY about of the compression flange. IY of the compression flange divided by IY total. C sub B for cantilevers, if the free end is unbraced, is always 1. Always 1. Okay. So what's going on here? When a moment diagram is constant, what value should we get? C sub B is equal to 1. The moment diagram is not constant. What value should we get? Greater than 1. Good answer. And now it depends on how non-flat it is. We could say that the majority of this moment diagram is still pretty flat. Pretty flat. We have non-flat out here. We get about a 14% increase in strength. You with me? Your moment diagram gets really non-flat. Hey, it's the same moment diagram, just moved down. The thing about this is really important. You need to pay attention to this. We have some zones where the bottom flange is in compression. That's what negative moment means. And some zones where the top flange is in compression. So now we have the ultimate fight. The ultimate, I want to buckle. No, I want to buckle. I want to buckle. No, I want to buckle. What ends up happening is they end up helping each other. Top helps restrain the bottom helps restrain the top. The capacity goes up even higher. Does that make sense? Now, you may, in your careers, run across people that see problems like this and want to call this L sub B, and that is dead wrong. That is dead wrong and will kill people. Okay? And there are people that will do things like this, and they'll say, oh, I'm going to use this as my L sub B because that's my area that's actually in compression. They'll say, oh, I'll use a C sub B 1 just to be conservative. That's wrong. Okay? If you luck out and your building doesn't collapse under the loading, it's because you just got lucky. Okay? And you don't want to live your life just getting lucky. Okay? It's not your job to be lucky. It's your job to know what you're doing. Okay? Okay. Any questions about this in general? Okay? That's cool. So now, there's some values that I have tabulated here of different C sub B's. There's actually a table in your book that's got some different C sub B's in it. There's actually a problem down here at the bottom where I've recalculated a certain C sub B value just to show how it all works. Okay? You should know how to do C sub B's. Shouldn't be hard. Okay? Now, let's flip over. Let's talk about a very, very important case here. I'm going to talk about a beam with braces all along my top flange and a load on top. Is this braced? A brace. What's L sub B? What would you consider L sub B to be? What's that? The length of the beam. How come? Well, it's going to depend on what the moment diagram looks like, right? Let's say the moment diagram looks like this. Okay? What are you going to use for L sub B? The length of the beam. How come? Well, there's a brace here and a brace here on the top and bottom. There's braces here on the top. And did we say braces on the top were effective braces? That was the review today, right? Were braces on the top flange only effective braces?
Not whenever it's the moment's being distributed like that.
Even if the moment's up. Even if the moment's up. I mean, we're talking about a complicated moment diagram. But let's say I change the moment diagram where the moment diagram looks like this. Are those effective braces? Then it comes down to, it depends how deep the beam is, remember? I said if the beam was deep, then those are not effective braces. You with me? Okay, so now let's go back. Let's change from this. Now let's go to this, and I'll ask the same question. Maybe I'll get the same answer. Are those braces effective? No, they're not. They're not. They're not. But if you go and ask 95 to 9% of practicing instructional engineers, they will tell you that L sub B is 0. Or the L sub B is that distance. Distance between the braces. That's the definition of L sub B. That's what you're taught. It's the length between the braces. Most people don't go to graduate school. And if they do, most people don't talk about effective bracing. Okay? Okay? Make sense? Okay? So, what L sub B should I use, though? Probably the entire length, right? And the answer I'm going to tell you in this class is you're going to use the entire length, but you're going to use a different C sub B. This goes back into kind of that same thing we were showing before. It's almost this exact same scenario as this. This idea where we've got negative moment, we have positive moment, okay? We only have braces at the end. We knew what to do here, right? What L sub B do you use here? The entire length. So this is the same problem as this, only someone has put braces on the top. Now, when does that ever happen? Does anyone ever know when something like this happens? Concrete slabs. What else? Good answer. Roof truss. This happens in every building. All the time. So to say this is a special case is wrong. Okay? This happens all the time. All the time. And people commonly use L sub B equal to 0 or L sub B equal to a very short number. And for a shallow beam, that's not that big of a deal. Okay? For a deeper beam, this can be a big trouble. But we're going to talk about how to do it right. You will often hear, or not often, you will sometimes hear engineers call this the L sub B. And again, that is dead wrong. That is dead wrong. Wrong, wrong, wrong. Don't ever let them do it on your job. Okay? So, what we're going to do is we're going to come up with a different C sub B factor. A different one. Different one. And we're going to first say if neither end moments produce compression on the bottom flange, neither end moment produces compression on the bottom flange, okay, then we don't have to worry about this, although I say there is no buckling. That's not exactly true. If it's deep, if it's a deep beam, we can still have side sway web buckling. Okay? So if it's shallow, we're okay. Case 2. When one or both end moments produce bottom flange compression. When either one of these end moments produce bottom flange compression, or a negative moment, then you're going to use this equation. This is a new CCB, different CCB equation. And there is no cap. Well, I say there's no cap. I mean, you're still going to have the phi m sub p cap. Okay? But on the previous page, we capped C sub b at 3. Okay? Okay? Or m sub p, whatever that is. You know, whatever. If that helps you remember that, you know, can't ever gift you above m sub p. That's a given. So there is no cap. You still have the phi m sub p cap, but there is no cap on the true value. Right? Like 3. So we're going to use the sign convention above. Now, is that different than we did before? Yes. What do we use? Previously we used absolute values. Now we're using this sign convention. Okay? These are negatives. These are positives. Okay? Everything above is a positive. Everything below is a negative. MO is the end moment that produces the largest compression stresses on the bottom flange. The largest negative moment is M sub O. M sub 1 is the other end moment. Could be positive. Could be negative. MCL is the centerline moment. Okay? You're going to take M sub 1 equal to 0 if M sub 1 is positive. This means that M naught, the left, plus the right, has to be between 1 M naught and 2 M naught. If they're both the same, then the sum would be 2 M naught, right? If this is lower, if it becomes positive, then we just use 1 M naught. If it's lower, it'll be somewhere between 1 M naught and 2 M naught. C sub B is used with M naught, to check lateral torsional buckling. And you use M max, whatever that is, for all your other checks that you have to do. Does that make sense? Okay. And then there's some examples, which we're not going to go through, but here's the one with a negative moment on both sides. And look, I got a C sub B equal to 1. Hey, it's the same as the equation. So now I have a negative moment on one side and a positive moment on the other side. Okay, it looks something like that. Calculate a C sub B factor. I get 5.67. So I'm going to take 100 kip feet, and I'm going to compare it to 5.67 times my lateral torsional buckling capacity. But I'm going to use 200 kip feet to check for hinge formation, or M sub P, against phi M sub P. I can still have a plastic hinge formation. Still have to check that for phi M sub P. But for lateral torsional buckling, check it versus 100. Okay? You don't get to just disregard plastic hinge formation in other parts of the girder. What this allows you to do is check for this to cause lateral torsional buckling issues, and the rest of the girder for other things. And then we have this bad boy. So when does this happen? This happens in continuous beams. With concrete slabs on top, with roof trusses on top, with roof elements on top. It happens a lot. Okay? Happens a lot. Okay? So now let's talk about this one. Uplift, or suction load. When does this ever happen? Seismic, no. Not usually. I mean, maybe. I mean, you do have a vertical component, for seismic, but it's not a lot. But you're on the right track. What other events are there out there? Wind, suction. Happens all the time in structures. Uplift. Okay? So on an uplift type situation, our compression flange is down here. And this is something that's very rarely checked. Okay? But is often the failure mode in structures from large wind events. Okay? You'll see this flange buckle and you'll be like, I never checked that. That's not in the manual. Okay? It's not. You're right. It's still your responsibility as a structural engineer, though, to understand and think about what could happen to the structure. Okay? So, we have an uplift. Now we got a negative moment here, and positive moment, and positive moment. M naughts are end moment that produces the smallest tensile stresses or largest compressive stresses on the bottom flange. The largest positive moment is what we call M naught. The largest positive end moment. I.e., the least algebraic end moment. Least algebraic. Okay? So, this is M1, this is M naught. It's lower. It's closer to 0. This one's 0, so it is M naught. This one's more negative. Pardon me, it's the... Let's see. Yeah, that's right. It's the least algebraic end moment. The largest, the most negative, closest to the negative infinity. The one that's closest to negative infinity. How's that? So that's the lowest because that one's more positive. That's the lowest because it's closer to 0. That's the lowest because it's closest to negative infinity. Okay? And again, there's no cap on these C sub B's except for, you can never get a, phi m sub P. That's still a bad boy. So if M naught, M1, or M max do not produce a compressive stress on the bottom flange, and there's no buckling, you just go ahead and check M sub P, is what they say. I still think that's not totally true. If things are really deep, you can still have side sway web buckling, but that's a different check. When both end moments are positive or 0, that's like this scenario. When both end moments are positive or 0, use this, C sub B. Check C sub B times the lateral torsional buckling with the largest moment that produces compression on the bottom flange. That's going to be with negative 150 kip feet. Okay? This one's going to be it with negative 100. When M naught is negative and M1 is positive or 0, M naught is negative, M1 is positive or 0, you're going to use this equation. A little bit different. Believe me, it's better than a 5-page differential equation. Okay? You're going to use this equation. So you're going to calculate this, and again, you're going to use this C sub B with minus 180. That's minus 180. When both M naught and M1 are negative, you're going to use this equation. And then you're going to use it with the largest moment. The largest moment in this case would be minus 100. This is not hard. It's not hard at all. It's easy. It's just complicated. Okay? Now, let's say you calculate these capacities and you find out you have an issue. It's not satisfactory. How can you improve your buckling capacity? What's that? Shorten the member. How can you do that? Shorten the ends. You could. How else could you do it? What's that?
You cut it in the middle and make it like 2 short.
It's not the best way to do it though. But that's you could cut it in the middle and make it simply supported beam, 2 simply supported beams or whatever. I like where you're going though. Instead of cutting, what if you put a brace? Where would you want your brace to go? On the bottom flange. The top and the bottom. And that's why you'll notice when a brace is done correct, well, I hate to say it correctly, but if you brace the top and bottom flange, you don't have anything to worry about. You're good. It's a brace. Right? It's only when you only brace one flange is when you start to run into some problems with this. That makes sense? And if you have a brace top and bottom here, it doesn't matter whether the wind's going up or whether the wind's going down. You got a brace here, you got a brace here, you got a brace here. You're good. It's only in these circumstances when it's say like, oh, I don't need to brace that. And you might even not even think about it because really we have a beam here. This beam's got some kind of whatever roof material on top that we're trying to rely on to be a brace. That's what you're really doing. And you'd say, well, why do I need a brace down here? Brace down here doesn't do me any good. Well, it does, though, in combination with the top and the bottom. Okay? All right? Okay.